We saw three techniques to prove that a given function is continuous at a point A. Two of these conditions, the epsilon delta definition and the sequential criterion, were definitions of continuity. The third, using limit theorems, was not really definitional, but it helped us prove the continuity of certain functions. Now the question is, given a function f, how will we prove that the function is not continuous at a given point A? To show that it's not continuous at a given point A, we have to show that the function fails the condition of continuity. In other words, we have to show that the negation of that condition is valid. Therefore, to be able to prove that a function is not continuous at a point A, we will have to understand the negations of the definitions of continuity. And we have so far two different definitions of continuity. The first is the epsilon delta definition, which states that given any epsilon greater than 0, there exists some delta which is greater than 0 such that norm of x minus a is less than delta implies that norm of f of x minus f of a is less than epsilon. If this condition is satisfied, then f is continuous at A. This is one of the definitions, the epsilon delta definition. The other definition, called the sequential criterion, states that given any sequence xn that converges to A, f of xn also converges to f of a. These are two equivalent definitions of continuity, and to show that a given function is not continuous at a point A, we have to show that either this fails or this fails. In other words, the negation of this statement or the negation of this statement is true. That's what we will need to prove. And both these techniques will be useful in certain situations. So let's try to negate both these statements. Let's go one by one. First, we will look at the epsilon delta definition. The condition states that for every epsilon greater than 0, something is true. Therefore, the condition fails precisely when there exists some epsilon greater than 0 for which this is not true. But what is this? This statement says that there exists some delta greater than 0 such that something holds. When does this fail? This fails if there does not exist such a delta. In other words, whatever delta greater than 0 you take, this does not hold or this fails. But this fails when this is true but this is not true. In other words, if there exists an x such that this is true but this is not true, then that also fails. Therefore, we can write this as there exists an x such that norm of x minus a is less than delta and norm of f of x minus f of a is greater than epsilon. Let us repeat. A function f is not continuous at a point A if there exists an epsilon greater than 0 such that whatever delta you take, you can find an x such that norm of x minus a is less than delta but norm of f of x minus f of a is greater than epsilon. Let us now try to negate the sequential criterion. The sequential criterion states that every sequence that converges to A satisfies some condition. So its negation would say that there exists a sequence converging to A which does not satisfy the condition. That is, the negation of this statement has the form there exists a sequence xn converging to A such that f of xn does not converge to f of A. That is the negation of this statement. Let us repeat. A function f is not continuous at a point A if there exists a sequence xn that converges to A such that f of xn does not converge to f of A. Let us work with an example and make sure that we have understood this idea. Consider the function f from R2 to R2 defined as f of xy is equal to xy by x square plus y square when x and y are not both equal to 0 and half otherwise. Notice that we have to define it in two cases because this expression does not make sense when x and y are both 0. It has the 0 by 0 form. Thus, we had to define it in two cases. Now, by techniques we have learned so far, it is easy to show that this function f is continuous at all points except 0, 0. We can now show that at 0, 0, this function is not continuous. We will show this using both the conditions that we had seen earlier. The first condition said that there exists an epsilon greater than 0 such that whatever delta you take, you can find an x such that norm of x minus a is less than delta and norm of f of x minus f of a is greater than epsilon. So the important part is to find out the correct epsilon. For this, notice that if you take any point on the x-axis apart from the origin, then its image will be equal to x into 0 by x square plus 0 square, which is equal to 0. And notice that norm of f of x comma 0 minus f of 0 comma 0 is equal to mod of 0 minus half, which is equal to half. Now notice that we can make the point x comma 0 as close to 0 comma 0 as we want. However, norm of f of x comma 0 minus f of 0 comma 0 will never be less than half. So if you take an epsilon that is strictly less than half, then we will have what we require. So in particular, let us take epsilon to be equal to 1 by 4. Then notice that for this epsilon, whatever delta you take, there exists a point, namely delta by 2 comma 0, such that norm of delta by 2 comma 0 minus 0 comma 0 is equal to delta by 2, which is less than delta, and norm of f of delta by 2 comma 0 minus f of 0 comma 0 is equal to half, which is greater than epsilon. Thus, we have proved that this function is not continuous at 0, 0. Now, it's natural to ask if this function will become continuous if we define the value at 0, 0 to be equal to 0. Unfortunately, it will still not be continuous. This is because if you take any point on the line y is equal to x, then the value of the function at this point, assuming that x is not equal to 0, is equal to x square by x square plus x square, which is equal to half. And this is why I had defined the value at 0, 0 as half. And of course, you can find such points that are arbitrarily close to the origin. Therefore, the continuity has to fail. In fact, it can be observed that as you approach the point 0, 0 along a line of slope m, you get different values depending on the slope. For instance, the value of the function f at x, mx is equal to x into mx, which is equal to mx square divided by x square plus m square x square, which is equal to m by 1 plus m square. And this idea of approaching the origin along different lines is often useful in proving that a given function is not continuous. Now let us use the sequential criterion for continuity to show that this function is not continuous at 0, 0. This condition states that there exists a sequence xn converging to a such that f of xn does not converge to f of a. So we need to construct such a sequence. Now the idea is that we observed that if we approach the point 0, 0 along different lines, we get different answers. And a point on a line of slope m looked like x, mx. So if you want to take a sequence of points that converge to origin in this line, you have to ensure that x goes to 0. In other words, we need to find one sequence that converges to 0, and our favorite is always 1 by n. So we can consider the sequence xn is equal to 1 by n comma m times 1 by n. Then notice that xn converges to 0, but f of xn is equal to m by 1 plus m square. Now this is a constant sequence, so it converges to m by 1 plus m square itself. So in particular, if m is equal to 2, then m is equal to 2, then f of xn converges to 2 by 5, which is not equal to f of 0. And thus we see that this function is not continuous at 0, 0. Now I want to warn you that you cannot always use this trick of approaching the point along different lines. Let us modify our function a little bit. So instead of taking xy by x square plus y square, we are going to take xy square by x square plus y power 4. Now notice that the value of this function on a point on the line with slope m is equal to x into m square x square divided by x square plus m power 4 x power 4. This is equal to x cube into m square divided by x square plus m power 4 x power 4, which can be written as x into m square divided by 1 plus m power 4 x square. Notice that if you treat this as a function of x alone, then xm square by 1 plus m power 4 x square converges to 0 as x converges to 0. Thus, irrespective of which line you approach through, as long as you stick to a line, you will always get the limit 0. But notice that this function does not look too different from what we had earlier. For instance, if we denote y square as z, then it has the same form as before. It looks like xz by x square plus z square. And we knew that that had some issues. More precisely, this is equal to half if z was equal to x. But notice that z is equal to y square. So we will have a problem if x was equal to y square. That means if we approach the point 0, 0 through the parabola, then we will have a problem. More precisely, the sequence 1 by n square, 1 by n converges to 0. But if you look at f of 1 by n square, 1 by n, that is equal to 1 by n power 4 divided by 1 by n power 4 plus 1 by n power 4, which is equal to half, which does not converge to 0. So the sequential criterion fails, and hence this function is not continuous. Let us iterate what we have observed. Even though the technique of approaching the point along different lines is useful, it is not a foolproof technique. In general, we have to be innovative and we have to make guesses and then try to prove what we have guessed.